أستاذة هبة تامر، صوتي مسموع؟ محمد؟
تمام يا عمر.
كله تمام؟ الصوت واضح؟
كله مية مية. جميل.
طيب خلاص، we'll start in 10 minutes. This process, when you gotta follow this process, it's the process that basically will solve everything. What is that process? As you would have thought, it is, here we go, Scrum. Many people basically think that Scrum is the answer to everything. We do everything by starting from a backlog. The backlog results in sprint backlogs. Sprint backlogs result in processes, planning, meetings, retrospectives, and give it an answer. Now, if you look at all these roles, there is one very fundamental role that is missing, that is not given the respect it deserves. When we talk about team members, stakeholders, users, product owners, scrum masters, there is no place here to basically highlight the importance of the architect, the testing engineer, the developer, the DevOps engineer, and so on. The result of that, the idea that Scrum treats team members just as team members is a bit disturbing for me, while it treats the Scrum Master, who's for all intents and purposes someone who's not, it's not that he's not needed, but the technical know-how on how to put a design drives the planning of a project. The other thing is when we look at sprints, the assumption here that a sprint encapsulates many streams, the design stream, the development stream, the testing stream, the stream that's trying to come up with support scripts and documentation. In the absence of a real design, all these streams going into this magnificent unit of fictitious time called the sprint get lost in translation and implementation. So, what skill set do you need? Today, it's kind of funny for me because when I look at job sites, this is what jobs look like for me these days. You gotta know everything. You gotta be what's strangely called the unicorn, or as they call them in these job descriptions, full stack developers. Full stack developers need to be good at JavaScript exactly the same way or at the same level they are with T-SQL, maybe with a bit of discrepancy. We expect this someone to know everything, to basically be able to code websites all the way from UI to backends to databases, integrate with cloud platforms, go from Google to Azure to AWS, utilize all the products, utilize all the libraries, be familiar with at least 3 or 4 programming languages across the board. Now, I don't know about you, but I have never run into a person who can write or code in JavaScript exactly like he can in SQL Server or T-SQL. You're always compensating. So we are lost in a world where we're expected to have all these skill sets. And the only analogy I can come up with is imagine the one person who can install a kitchen, do the electricity, install the walls, do the design for the house, do the plumbing, make sure that he can do the tiling, the painting, everything in a house. We would never expect that, yet we will always kind of talk about it in the software world, not giving it the respect it deserves. And the result is this crazy world of Stack Overflow driven development, where we start going to Stack Overflow for stuff that we don't know. We copy paste, hope for the best, and let's just say that if it breaks, we hope the tester picks it up in testing phase and make sure that we fix it. Why? Because again, there is not the one human brain who's going to be able to deal with all the pressures, all the technologies, all the budgets changing, all the requirements changing, all the priorities changing, all the velocity changing. So from this perspective, we want to go on and figure out what is it that we're trying to produce. And for all intents and purposes, it's this. We're trying to produce a complex system. The difference is while the system is complex by requirement, it doesn't mean that it has to be complex in design or implementation. So when I look at this screen, yeah, this might look a bit abstract, a bit nice. Maybe it's something I'd like to hang in my wall. But the reality of the matter is that it is not what I think about when I think about software. In fact, when I look at this, I think about one thing and one thing only, is the spaghetti code, right? The part where we all end up with. So after all this gloomy introduction, what are we saying? We're saying that we need to turn architecture into engineering. This is engineering. I don't care what it's called, architecture, design, producing blueprints, whatever you want to call it, it is a form of engineering. And for engineering, there are principles, there are disciplines, And there are paradigms in practitioners of engineering that we need to talk about today. So let's start with the first aspect, your skill set. The stuff you can actually do and find on Google, right? Your skill set is going to be precise. When you are an architect, is it mandatory that you be that you are also a good coder? Absolutely not. But it is a big asset if you are. If you're an architect, what is your main asset? Divide and conquer. Your ability to do decomposition, your ability to come up with solutions for complex problems and then organize these come up with simple solutions for complex problems and then be able to assemble your blocks into a bigger solution that solves the entire problems of the domain you're in. This idea of unicorn that you're going to know everything, you won't. There are some principles you need to know. And when you go into a job and they tell you you got to know HTML, front end, ASP.NET, service bus, blah, 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 tell them that this sounds like a job for Superman, right? Because no one is able to do it all. Your principles that you practice and the process that you follow will produce artifacts that then people who are experts in UI, in backend development, in database can go about their work, right? So why did I say coding is an asset? There is a process to architecture. Architecture is 33% of the software project. So from that perspective, if we're talking about 33%, what does that 33% contain? Number one, design. Design. Meaning that you actually look at the problem and think about it from an architectural engineering perspective or angle without sitting down and attempting to code before you even know what it is that you're going to code. Number two is prototype. If it doesn't work for you, it doesn't work for anyone else. But hang on a second, you said coding is non-essential. Yes, that's true. If you don't know how to code as an architect, you're going to have to get someone to help you with the prototype. Hence, I said that if you are an architect who codes, then you have a big asset, and that is you don't need anyone to prototype it yourself. Number three, feedback. Feedback is very important. As architects, we tend to get lost in that notion that we do everything properly and we are the best at what we do, and this causes a lot of problems. Get feedback from your developers, from your customers, where it matters. And last thing is, yes, we haven't written any code. We only have a prototype. Let's test it. Let's establish a new paradigm where we test our designs, where we scrutinize the designs, where we actually ask people to come and look at our designs and talk to us about how these designs are relevant, accurate from their perspective or inaccurate from their perspective. So the tools include a code editor. The tools include a lot of things. You can have modelers. You can have Visual Studio and do some code, or Visual Studio Code, or Notepad++, whatever it is that you need to be able to code and model. When we model, we can use designers, we can use UML, we can use scraps of paper, as long as it's stuff that you can save until you produce the final artifacts of your model. But what does your model actually show? What is this model you're trying to produce? And again, let's break things down. We've named it a lot of things, but for all intents and purposes, what you are trying to produce is artifacts that represent a component design. A component design, a bunch of components that sit together to form a system. We can call them objects. We can call them services. We can call them microservices. We can call them Lego blocks for all I care. The point is we are assembling multiple mini solutions and components into a bigger beast that basically supplies the functionality needed by the software built for a specific domain. Okay, so we got our tools, we produce component design. Let's talk about what am I using these components for? What is my mindset with these components? What is this architecture? Is it only about supplying functionality? If it's only about supplying functionality, then you've missed something very important, is that if there is anything that the last 30, 40 years have taught us, is that users will always change the requirements and change their minds. In fact, in architecture, as in engineering, change is the only constant. So basically, we need a component design that caters for change. Do you see now how this is a paradigm shift from you simply building a design that will deliver the functionality? It's not like that. It's the idea that you're building a design which will respond to change. So what are the changes? Changes in requirements, changes in hosting platforms, changing in ever-changing technology frameworks, changing in the way exposure is done of your functionality, whether it's on a mobile app or on a web application, changes in responding to browsers being updated almost every year, with 4 major releases at least, changes in the paradigms on how people like to interact with their applications, changes in how we scale up and scale out data and data storage, right? We've got a few rules we're going to live by, and we've got a new skill sets to think about to be able to establish that component model. Number 1, high cohesion and low coupling. High cohesion means that objects that are related in functionality or are cohesively required to be within the same proximity in your software in order to deliver a functionality needs to stay together. And low coupling means that if there is an organized, modularized organization of your components, you are able to change one without changing the other. It means that we try to make our dependencies on abstractions instead of concrete implementations. All right. So from that perspective, we're looking at, again, keeping the components that belong together as much as possible close to each other, and components which have dependencies to be dependencies on abstractions and not implementation, hence achieving low coupling and hence allowing for easier change. Number 2, going back to basics, object orientation. Object orientation did not go away. The concepts like polymorphism, inheritance, designing around objects, this has not gone away. This is still the core for business applications. Even with the rise of functional programming and functions as a service and all of that sort of stuff, object orientation is still important. As an architect, it doesn't matter what functional or non-functional technology you use. Your design is usually still based on objects, and these objects are either real-life entities or real-life descriptors and their relationship with each other. The next one is design patterns. You don't need to reinvent the wheel. Design patterns are there. Some people have figured it out. And if we figured it out, and if we get to learn them, we get paid for it. This is pretty cool. Now, whether we are talking about the gang of 4 design patterns, which you can find on dofactory.com, or whether we're talking about the cloud design patterns, the ones you can find on Microsoft's MSDN, we're still talking about patterns. Patterns are tools that you use, ways that other people have solved very specific problems. The more patterns you know, the more better solutions that cater for change are going to come to you as you're coding. But this becomes a problem because design patterns are about the evolving of your code, right? I mean, people look at problems and then they think to themselves, what design pattern I'm going to use here? But there is another angle that is even more important than design patterns. It is how do I make sure that my code does indeed respond to change and does indeed have low coupling and high cohesion? Many people wonder, I want this, but I don't really have a definition or tools for it. When the definition is hard, you have to endeavor to learn it. But when it comes to the tools, it's actually there. Solid design principles. Solid design principles, if applied properly in your application, are the way that you would guarantee that your application is not tightly coupled and it is indeed responsive to change. The S stands for the single responsibility principle, where we say that every component in our application can change only for one reason, as it has one reason to exist. The O stands for the open closed principle. And that means that any piece of code that is shipped is closed for modification, but open for extension. The L, the Liskov substitution principle, which basically says if there is a function that takes in a concrete implementation of an abstract object, then that function should be able to receive the abstract object or any of its implementations without a result, without a change in output or a change in algorithmic behavior. The I, interface segregation principle. We've all heard about that one API that rules them all. Give them the one API and it will be used by everything, by mobile apps, by internal employees, by outside customers. Interface segregation basically says, while your core of your algorithms and your execution stays the same, it is essential for you to give or produce interfaces that are customized around how they're going to be used. Meaning, and this could mean very, very expensive discussion with your stakeholders, but an important one nonetheless. Meaning that if you're going to talk from a purist perspective, you need to provide an API for applications as well as an API for your mobile apps. Yes, I know, expensive, but it's a discussion that needs to be had. And D is dependency injection. My entire interactions across all my application is built on abstraction. Interaction with abstraction. Relationships with abstraction. And implementation is only injected at runtime, but the relationship between my components is only done by abstraction. So take note down, solid design principles, and we can expand on that in future sessions, showing exactly how solid works, what are the examples on each one of them, and how does it actually help you on day-to-day. So the other question that I get a lot is, what book? What's the paradigm? This form of engineering you keep telling us about, what is it? Like, what can we go back to a book and get sort of a catalog on how to do these things? I tried. God knows I've tried. I've tried looking for a lot for the one book that rules them all. I tried looking for the one paradigm that rules them all, and the reality, such a thing does not exist. When you study philosophy, you find yourself needing to go and read about Descartes or Kant or Schopenhauer or Spinoza, and you need to go and read the different schools and different paradigms, and here is no different. But there is one book and there is one form and methodology of thinking that comes very close to being perfect. In my opinion, because I've practiced it for so many years and it's worked for such a long time. And that book is domain-driven design. Domain-driven design is a bunch of concepts and a bunch of artifacts that can be produced within a process to basically break down the complexity of requirements and produce artifacts to represent a solution for a complex enterprise system. Again, a bunch of tools, concepts, artifacts that can be produced within a process to represent the solution to a complex enterprise system. So what is this domain-driven design? I mean, me saying it's a bunch of concepts and artifacts is not enough, but it is exactly that. It is basically concepts that have relationships with each other. So I sit with my clients, I gather the requirements, then I apply the requirements to this diagram. I basically break the requirements into each concept in this diagram. This is the closest one. While it looks complex, it just needs investment in time so that you take your time to actually be able to understand every concept and its relation with the other concepts. But once you know it, it's the closest thing that we have today in the software industry to a manual to thinking about large complex enterprise systems. Okay, so domain-driven design, extremely important. And this is, again, we can run sessions in the future to do introduction to domain-driven design and see how we're gonna, we can tackle these concepts one at a time. Then we have some architectural, as well as having concepts and tools and relations, we also have patterns. More patterns, this time organizational patterns. CQRS, reads and writes. So what does CQRS stand for? Command and query responsibility segregation. What does it mean? That when you have a system that reads data and writes data, that you can have vertical architectures and patterns that do not necessarily line up, but in fact, they are optimized for what they are doing, meaning that the vertical side of my writes is optimized around my writes, my consistency, my indexing, my transaction, etc. While when I'm reading data from a system, it is optimized around the fastest access to the latest consistent projections of data that I have. Concept is not new, 1973, and it was called CQS, command and query separation back then. We might like to enhance the terms and terminology as we go, but the reality is this stuff existed a long time ago. Another pattern, event sourcing. It was years while everything was relational. Everyone used the relational database. SQL and Oracle, Oracle and SQL. That was usually the main things. And then we had MySQL come out, PostgreSQL come out, but still people thought about data in a relational fashion in all times. Event sourcing breaks that model and says, I will not store state, but I will store behavior. Meaning that instead of having a customer table with a customer record that is maintained until the end of life, what I do is I have a series of events: customer created, customer address changed, customer activated, customer bumped up to gold status, a bunch of events. And I use these bunch of events to create multiple projections showing me the state as a deduced value instead of as a value of a record that I'm just manipulating in a database until the end of time. Another one is microservices. Systems can get really big, and we can break systems. There is a concept here that we say that the more developers you have on a single piece of code, the more friction you have. Microservices is not an architectural pattern as such that it helps you break something that domain-driven design doesn't. In fact, you need domain-driven design, you need solid principles, and you need other tools to make sure that you've got enough components that you can wrap up as an API to basically create a microservice. So where does a microservice help, and where is the big hoo-ha around microservices? Is that once you have that component design, it can be developed, tested, deployed, and managed independently. It becomes a product in its own right. You want to look at good examples with this? You can look at the architecture behind Netflix. You can look at the architecture behind Spotify. You can look at the architecture behind Azure Service Fabric. A lot of architecture, a lot of big companies out there have used microservices to break down the process of developing their components. But please note that that does introduce a challenge. The challenge is, by nature, the minute you break a system into multiple components that are distributed over the network, you have entered the realm of the distributed systems, meaning your concepts about data consistency, transactions, and communication between these components have changed. There is a big difference between me exchanging data between components using memory and using the network. Between memory, where my failure rate is very low, and between the network where transient errors are very likely to happen. So this brings me then that my integration and messaging patterns become important. Because the minute I say I'm going to build distributed systems, I need messaging. I need forms of integration between these components. But not only that, now when we go to distributed systems, we also talk about infrastructure. We also have the concept of having multiple infrastructure pieces on the network. You don't need an MCSE to practice infrastructure in 2021, but you do need the least amount or the least skills to achieve good DevOps in a distributed system. So we went from problems to definition of the crisis that we have with skill sets, etc. We went into patterns. We went into tools. And this is like a bombardment of information that we're not done with. But stay with me. So far, we've went from breaking down the software, talking about tools, and then coming up to infrastructure where we're going to deploy this, the microservice, the CQRS, the domain-driven design. Someone has to cover the rest of this missing 33%. If we say architecture is 33%, and then development is 33% as well, or whatever percentage that is, what is left? Our friends in quality control. So our friends in quality control these days, the testers, will not take your "it works on my machine" for granted. You need quality control on distributed systems that basically outmatches everything that we did in the past. This concept of exploratory testing, where you give a machine a screen that could most probably be replaced with an Excel file, because all it does is CRUD and collect some forms and fields on a screen and basically put them in a database, does not cut it anymore. In a distributed system, testers have got to be very smart, understand the concepts that lay behind transient errors, failure recovery, redundancy and scalability. So what do we do beyond the infrastructure? Beyond the infrastructure, we need to give the testers and the developers a good story with DevOps. Now, don't get me wrong. Many of you that I see on the listeners over here have heard me say in the past, many people are overdoing DevOps. Many people are spending more on DevOps than spending on dev. By the same token, you need a minimal amount of automation that will make it suitable, that changes in code get reflected in testing environments as soon as possible and are available for testers to test. And we also need DevOps to manage a seamless process for production deployments. Do not go overboard, find the right ratio. And as an architect, you need to be involved in defining this ratio, in making sure in whatever you spend in DevOps is actually producing real ROI, and that you're solving a real problem. You got to report as an architect. If you don't establish a system where you're able to report, you have a big problem. I know many people will take this and say this is the Scrum Master's job. It isn't. It is actually the architect's job to come up with a design and a process for the developer and the technical team to basically be able to report. I fall into this trap myself, forgetting about the ability to report on design, on technical concepts that stakeholders find extremely hard. So yes, upfront, I try to come up with designs that I'm able to report on. And the last one, or maybe before last, is teach. Many architects today monopolize their knowledge. They think that if I know a few tools, that makes me a very niche resource, which means I can charge more, I can keep my job for a bit longer, etc., etc. It doesn't work that way. If the last 15 years have taught me anything, it is that the more I teach is the more I learn. I find myself learning from people I teach more than anything that I would have learned if I tried to monopolize my knowledge and not share what I'm learning. In fact, because of my sharing, I got to collaborate with some of the greatest architects in the world and have discussions with them that added to this very course that I teach today. If you learn something new, teach it and get scrutinized over what you know. That's the only way you yourself will find value and reward in your knowledge. There's no point of it staying in the closet or staying in the cupboard. And let's face it, if the software industry starts having a higher success rate across the board, it's better for all of us. Maybe then they wouldn't lose trust and try to replace us on every chance they can. Fallacies. You want to be a good architect, build yourself a framework. How many times have you heard that? This developer has become so good, we can now make him an architect. He managed to build his own framework. No, it doesn't work that way either. In fact, do not build your own framework. You do not need a new framework. There are millions out there. You can get one, customize it. You can create a little, assembly of things. Being an architect, it's far from building a framework. You want to become a framework developer, you need to be on the .NET team, on the Python team, on the Azure team, AWS team, where you're creating platforms for people to use. Do not build a framework by default for an enterprise business application where most probably every use case has been already solved from a technical perspective. All right. Fallacy again. Engineers like to solve problems. If there are no problems handily available, they will create their own problems. Do we all agree? I believe we do. The reality is sometimes things can get boring. You've heard me say it before that majority of the applications that are that we're being exposed to in our industry today are CRUD applications. And they can be basically replaced with an Excel file. An Excel file where we say, collect this data, aggregate this data, produce a chart and a report. That Excel file will most probably take a week to do. And at the worst case scenario. Meanwhile, we spend millions building Angular web applications on top of ASP.NET web APIs, on top of crazy Cosmos, Postgre, MySQL, SQL databases, which are supposed to deliver more value than that Excel file. So sometimes we get bored and we try to find more problems. And we try to create problems where we say, you know what? I can take this data and push it into the database. Or I can build this sandboxed API within Docker and make sure that it is multi-threaded and that all the threads, process this down to the minimal amount of ticks in order to get this data into the database. But really what you're doing is over-engineering what is already boring. Again, there's two things I say that will happen tomorrow morning. We're going to create a problem to be able to create a framework for it. So we're going to breathe oxygen and there'll be a new JavaScript framework. That's the reality. So what are some of the tips that you can create to help yourself on this journey? Create yourself a checklist. A checklist is very important in everything that you do. A checklist to your design artifacts, a checklist to what you're going to do in a day, a checklist to what you have to deliver for the developers, a checklist of the rules that you have to apply when reporting to the stakeholders, a checklist of the milestones, a checklist of the ceremonies, a checklist of everything. How do you scrutinize your design? Try to change it. Every time you come up with a new design, a new process, etc., scrutinize it. Scrutinizing with every method. You can scrutinize it yourself by trying to change it. You can get someone else to give you feedback or trying to change it himself. See how you would respond to it. The only way to scrutinize any architectural design is by trying to change it and measuring exactly how it responds to change. It might become tough sometimes. The domain changes. You kind of ask yourself, what reference point do I have to achieve all of this? And sometimes you get lost in your ivory tower that you forget that there is a market out there. And if you research what other people have done, you might actually get some answers. I am sure when they were building Azure, they were asking, what did AWS do? When they were building Virgin Airlines, they questioned how did Emirates do the logistics? And when they were building, stock trading companies in Australia, they were comparing it to stock traders in the States and seeing, can they do it better and does it work for our market? Startups. Many people go and create ideas and startups thinking that it's about being unique. It's not about being unique. It's about how to do it better. And you can't do it better unless you have a baseline to measure from. And the only baseline that you can compare and measure against is one that has been established already, and that one that is already out in the market. Do your research. If you want to do architecture, you need to do your research. And that includes research and tools and technologies that are coming up on a daily basis. So finally, I say, for this section, we can't solve problems by using the same kind of thinking we used when we created them. That was Albert Einstein. Things are different. Everything you heard from me in the last 50 minutes does not, under any circumstance, is not included in any book, and you will not get it in the format it is, because I struggled to get it in the format it is in today, and I had to go and search for it. And I think it's concepts like this that needed to be taught at universities for us to actually have an architecture curriculum that people can respond to and know the principles of architecture before going into the market and becoming architects and engineers. So guys, this was the end of the first section, and it's the longest section. The next section we're going to touch on is two sections are going to take half an hour. These are requirements and estimates, and also standards and decomposition methods. So we'll take a 5 minutes break. If you have any questions, you can put them in the chat box. I will answer the questions, and then we're going to get to requirements and estimates and decomposition methods next. And hopefully that will take half an hour to 45 minutes, and we'll take a question time of 15 minutes and we'll be done. Thank you, and I'll wait for your questions. All right, guys, I'm back, and we have a question from Samer. How do software architects deal with the problems of migrating from legacy systems, given the fact that these systems usually do not have an architectural documentation? Excellent question. Maybe a bit too advanced, but let's go very briefly into it. Number one is we have to attempt to gather all possible documentation and information we can discover from these legacy systems, meaning that a lot of the time that we need to actually discover what the legacy system or how it was built on our own by technical analysis. That's number one. Number two is you need to treat the legacy system as if it was another component within your current design. Only thing, it is a component that's going to leave eventually. So how do you do that? You wrap it into something. And that something is usually, people say, just put an API in front of it. That something is actually got a name. It is called an anti-corruption layer. I'm going to put it on my screen. If you Google anti-corruption layer, and you will find that that is, in fact, the paradigm that we use for encapsulating old systems, right? So working with legacy architecture, you'll find that here is the old system. Here are your new microservices or whatever you want to call them. And usually we put in front of it an anti-corruption layer. An anti-corruption layer basically helps transfer or transform the data and the processes at the time of moving the legacy into another system without having to disable or migrate the whole legacy on day one. So what you do is you create an ecosystem which includes both old and new, and slowly, by discovering the process and data, and by allowing the anti-corruption layer to translate between both systems to make it look like you've got a unified process, you slowly move from the legacy into the new system. Okay, now there are obviously a lot of techniques and a lot of concepts around that, but I just wanted to give you an idea, Samer, that this is how we usually think about it. Okay, I shall. Cool. So there are no other questions. Let's continue. The next slide, with its title, speaks about the dark art, requirements and estimates in software projects. As an architect, you're very welcome. As an architect, part of what stakeholders struggle with is how much is it going to cost? And how long is it going to take? That is a very hard question. But let's talk about how we can get there. One method of how we can get there with scientific approaches. The rule says you cannot estimate and you cannot build what you do not know. Meaning that if your requirements are not clear, and you don't have a clear vision of what the result of your effort is going to be, you cannot get to a plan. And if you can't get to a plan, you definitely can't get to an estimate. So step one, and this step one is so important that Gartner says that it is responsible for at least 40% of software failures. It is the requirement definition. How do we define a use case? I know a lot of young people that can potentially be listening to me saying, what the hell is that? We're used to user stories, etc. Let me tell you what a use case is. For me, it doesn't matter how you represent it, how do you document it. It's basically a collection of answers to questions. Number one, the actors. Who is involved in this requirement? Who is gaining anything? Who is the person who can invoke it? Who is the person who's actually going to be the if we consider this use case a movie, who's going to be the main actor? Number two, what is the scope? Is it only applicable to this subsystem? Am I only dealing with the marketing department in real life? Am I dealing with the logistics department? Am I dealing with the product inventory department? Who am I dealing with? What system areas are involved? Number three, the brief. Give me a high level. Give me a couple of sentences telling me what is this functionality achieving? Number four, stakeholders. Who are we making happy? Who is the person who's laughing all the way to the bank at the back of this use case? Who is responsible for it to work? Whose KPI does it go under? Number five, sorry, preconditions. Maybe there are things that need to happen before this use case can even take place. For example, can I, as a customer, purchase a product from your website if I don't have a customer account? If the answer is no, then a customer account is a precondition. Number six, post conditions. Minimal guarantees is what everyone is going to want to have to deem this functionality adequate and complete. But there are also successful guarantees where you get a bonus because you've given people not only the absolute minimum functionality, but you also give them some nice to haves, like that bubble screen that describes exactly how to do the purchase, or you put an ad in there as an extra because it basically allowed them to see other products which they can then purchase as well. Then we have triggers. Triggers are basically the events that are, or the things that need to happen, not the things that need to exist, such as preconditions. It's the things that need to happen in order for this functionality to start. Meaning, the customer clicks on buy it now. The customer clicks on checkout. The customer schedules an alert to go out. All of these are triggers. They can be real time or they can be delayed. They can be caused by users or they can be used by subsystems. Then we have the basic flow. The basic flow says that as a customer, I go in, I browse my catalog, I choose a product, I add it to cart, I check out. That is a major use case. Now, if you want to break it down, we say, as a customer, I want the ability to add a product to the cart. So I look at my product catalog and add it to the cart. But we always assume that this product is in stock. So I can just add it to the cart, when in reality, there are always alternate flows. Alternate flows are extensions to the basic flows that allow you to handle edge cases or cases that do not fit within the normal flow. Cases that do not fit within the normal flow. Now, guys, I understand what you're thinking. You're thinking that we as developers and architects never see this. No one is is ever giving us a document that has all of these? Well, my question to you, and are you still wondering why a lot of software projects fail? These, according to every academic paper, every Gartner report, every kind of structure you're ever going to create to a requirement, whether but please note this, any engineering project, this would be counting as the bare minimum. Now, I'm telling you, these are questions that you need to answer if your design is to really cater for what is required. If these questions are not answered, then my question to you is, why are we disappointed when we get the wrong result on the other side? Okay, so Omar went to Wonderland and got all his requirements and all the aspects of his requirements. What's next? Omar compares what he usually gets as who I want, what, so, that, why. As a student, I want to purchase a parking pass so that I can drive to school. This is what I'm getting today compared to this. Now, there's everyone starting to see the trend of where the problem is at. Instead of this, I get this. And the result expected from me is to produce the correct software as if to assume that I got this. All right. So let's move on. I've got my requirements. What do I do? Guys, we have to produce operations from the requirements. What do operations mean? Meaning that these bunch of requirements will not by necessity in the very first instance produce a model. Still, as an architect, I can't take these requirements and jump from requirement to model. Not just yet. There is one more step, because guess what? I haven't got paid yet to get a model or to even sit down and produce a model. I haven't even got that far, right? So we need to divide this into some operations. So what are operations? Operations are things that the software system is to do. Number one, the description of the operation. What is it? Remember, operations are what you're going to eventually pass on to your estimation team and your developers, eventually. Number two, what type is it? Is it a command, a query, or event? Aha. So now we go back to that concept of command and query responsibility segregation. We're saying that an operation is one of three types. Number one, a command, meaning I am asking the system to do something. A query, I am reading some data from the system based on some specification. Or number three, an event, which means that the system itself is signaling other systems or internal subcomponents that something has happened. I can very easily produce operations on a very high level from requirements if I get the requirements broken down as we saw them in the previous slides. Fields. And at this point, you don't have to produce a full-fledged data dictionary, but at least know that as these operations occur, they carry with them some data, and the fields specification of this data is important to know. Prerequisites. Aha, so we had preconditions over there. And now we have prerequisites. This is a prerequisite for a command, a query, and an event that can take place. Meaning that if I have a query that says, get me the sales report, well, the prerequisite for that is I got to have some sales data first. If I am to issue a command to complete a purchase, that means that I do have some items in the cart. These are prerequisites. And once you get to modeling, they help you a lot by creating what we call dependency graphs. And believe it or not, dependency graphs not only help you with estimation, but also help you with project planning when it comes to assigning tasks in order. Steps to consistency. When you do an operation or define an operation, there needs to be steps to consistency. If I am to complete a purchase, what are the steps to deem that purchase complete? When would I accept that this operation has completed? What are the steps to consistency in a query? Has this report been produced? Does it have the correct data and charting? Was the event triggered based on the condition that it's supposed to alert people to? What happens after the consistency? Do I need to signal another operation? Do I need to start another operation? Is this operation part of a workflow? Does it have any impact on external components? Like, for example, if I complete the purchase on my side, do I need to signal the fulfillment and shipping system? And what are the non-functional requirements for this operation? How am I gonna basically say that if an error happens, what should happen? If there is an error in the operation and it is very critical, how do I handle it? At what speed does this operation need to run? Many people have SLAs, saying, for example, that a certain use case or a certain operation or certain functionality within the application needs to run at a certain speed. And you need to have fulfillment of your service within certain boundaries. So from that perspective, we need these specifications specified to the developers so they can take it into consideration, or the architects so that they can design taking into consideration the non-functional specifications. And finally, when do I deem this operation complete? What is my acceptance criteria? So guys, the business analysts produce this. And once we have this, the architects need to produce this to pass it on to estimation and the developers. So the workflow, use case to operation, and what just happened? Work assignment. Oh God, do you see what just happened? Instead of you sitting there, once you actually get to the implementation phase and thinking, how am I going to assign this work? Well, I have an operation list. I have the dependency graph between these operations. Now I can assign one developer to one operation. In fact, just by doing this notion, this process from going from requirement to operation, what did we just do? Not only did we feed the idea that we can come up with a plan on how we're going to assign the work to developers, but also we can come up with some estimation rules. Number one, progressive commitment for design, saying, hello, I've got these operations, or I need to come up with these operations, or I need to do a model. Guys, this cannot be fixed priced. Let's go on a progressive commitment where we go with you on a time and material engagement until we come up with a design or a preliminary design that we can build on. Number two, one operation equals one man day. What? We actually have an estimation. Now, this is your basis. You can go up from that. You can even say that one operation means one man day on the back end, but 2 man days on the front end, because we know all these JavaScript goons will need time to finish their screens. So you can come up with any formula that works out for you based on an operation. Now let's look at the cost. What did we say at the beginning in the first hour? Architecture is 33% of the cost. So architecture at 33% of the cost of the total operations defined so far. But we also said that the testing cost covers the rest. So it's 33% of the operations so far. So this gives us a formula. And the formula could either be just a bare bone, like you see it on the screen, or at this point, I can provide a contingency. The formula plus the contingency at a bare minimum gives you some science to talk to people instead of you going and saying, I believe it's going to take 3 months, just to realize that what you just signed up for takes 3 years. Going again, if you think this is hard, let's look at it again. You're going from requirement, a use case that answers all your essential questions, to operations developed by the architect. Automatically, you get yourself a nice workflow for work assignment, and you get some science to create an estimation. All right. So this is the second section. And the third section will be standards and decomposition. Again, it's 6:25 p.m. here in Sydney. We'll give 5 minutes. Please put your questions if you have any in the chat box, and we'll be back in 5. All right, we're back. Amazing question, sir, as usual. So let's see. Given that software architecture may lead to too much big design upfront, what's your views about concerns that software architecture contradicts with agile development principles? And how do software architects balance the trade-offs between upfront design and agility? Agility and design need an unholy marriage established, and I'm going to be at the wedding. Now, here's what it is. Do you need design upfront? Yes. I would, at the moment, Scrum caters for that by calling it the establishment sprint, or the initiation sprint, or the initialization sprint, whatever you want to call it. At the end of the day, that sprint can go anywhere from 2 weeks up to 6 sprints spanning 3 months. But the reality is design needs to be ongoing, meaning how do we marry agile and architecture? We marry them by introducing the concept of design sprints, meaning that if there is a sprint, the sprint is split into multiple streams. There are only multiple streams of sprints running at the same time. One that is only responsible for design, and it actually beats the developers by being 2 to 3 sprints ahead of them. And the other one is the development sprint that needs to follow. Just like Scrum at the moment is coming up with peace, in the sense that it is following the idea of streams with testing, saying that you develop in one sprint, you test in the next sprint, developments are fixing and producing more functionality, then the sprint comes up for testers again. And this is what I'm saying. Just like the marriage is finally coming to some kind of structured process when it comes to testing, we need design sprints as something that we take into consideration seriously, and it becomes part of the ecosystem, just like testing is. As for the second question, as per TOGAF, we have application architecture, data architecture, technology, and business. Is that only with TOGAF? I thought we have more. Anyway, how to put in place each one of these without overlapping each other in such a use case? That comes up something just like the design pattern is called chain of responsibility. There is a hierarchy of responsibility that TOGAF speaks about, meaning a solution architect is at the bottom of the food chain. He's usually responsible for a single domain, and he's got to deliver services for that domain properly. An application architect is responsible for integrating more than one domain by looking at the integration points between those domains. So he can basically look at an integration between the marketing and the fulfillment department, or the sales and the inventory department. Now, when it comes to an enterprise architect, the guy at the top of the food chain, he looks around all of these integration, all of these domains, and how to organize them at the very top. In order for him to do that, he's got 2 architects that stand vertically across from everyone. Those are usually the data architect and the technology architect. The data architect is responsible not only for giving guidance on the silos of data that are available in every service, but he's also responsible for creating a master data set, or an MDM, master data management, or master data manager. These days, usually this is brought to reality by the use of data lakes, where data lakes are basically populated with all the data silos, with data from all the data silos in an enterprise or in an ecosystem of software. And then the data from the data lakes is then passed into other subsystems and other data aggregators to produce reporting. The technology architect is also working vertically across all of these layers, across the hierarchy, to make sure that technologies are at least producing no more tech debt that can be handled. You got to remember, an old technology might work for a new problem. The only problem you have is as technologies get old, they accumulate a measure of tech debt, meaning that you actually owe some effort to upgrade that technology or that piece of software. As tech debt increases, you might end up in a situation where an application is 20 years old, 15 years old, and it's considered ultimately a legacy that is very expensive to change. So the job of the technology architect is to make sure that the tech debt ratio or measure of the technology is not one that cannot be handled anymore. I hope I answered both questions. And let's move into standards. And this will be the last section of today's intro. And I hope you guys are enjoying it so far. All right. Now, what makes good software good software? How do we know that software is good? A lot of people will say, you should see this website. It's amazing. Or you should see this app that I've got on my phone. It does so many things. Now, that is all emotional. That all cannot be measured. So the question is, how do we measure if a software is done right or not? We did say that this is engineering. Engineering implies standards. So the question I came up to in like very early in my architecture journey is, do we have a standard? And guess what, guys? I found one. It's ISO 9126. It actually exists. An international standard just for measuring software. Is it good or bad? And it gives it multiple measures. So what does ISO 9126 say? It says the first measure of any software is a functionality. Is it suitable? Is it accurate? Is it interoperable with other systems? And is it secure? And is it compliant with all the functionality that the client has given us? Wow, that's a very good start. Tony, you got to tell me this thing. I mean, this is an extremely good start. This is a good start because we now have something at least to measure. Even if those measures are a bit gray, in the ISO, they are, in fact, detailed on how you're supposed to measure each one of these metrics. Not only that, this is a group of metrics. So this is the first group of metrics. It goes on from there. And I'll get to you in a second. Here we go. Now, what's the second group of metrics? Reliability. Okay. So let's look at these metrics. Is the system mature? Mature here doesn't mean it can go out and drink on its own. Mature here means, does it have the ability to change its requirements without breaking the whole thing? Deploying new technologies without having to rewrite the entire application. Fault tolerance. If there is a fault in the ecosystem, whether on the infrastructure level, whether in a bug, as a bug or a defect, or there is a fault somewhere in the ecosystem, can it tolerate it? And recoverability. Can it be recovered? The whole thing crashed. The data center disappeared. Everything went to smithereens. Is that recoverable or not? Usability. This one is nice. I found this one to be the most interesting because a lot of people will understand it, but this is what we always get. I wouldn't say always, let's not generalize, but a lot of people get this wrong. Yet this is the only group of metrics which is very easy to understand. So the first one is understandability, meaning if you look at the software, do you understand what it does? And do you understand how to get what you want out of it? Learnability, can you learn it on the fly? Or do you need a big knowledge base? Do you need a big manual? Operability, how much effort are you spending operating the software? How much brain power down to the idea of how many personnel? Do you have to call someone in the middle to get stuff done? And this fourth one plays with my heart a little bit, because attractiveness. If anyone would have told me that there is a metric about software that people actually measure with actual science, and it's called attractiveness, I would have been very surprised. Right? Yes, is the software attractive enough or not? And under this goes the section of compliance of 508. Is it attractive to you as much as it is for a colorblind person, for a blind person, for a person with no limbs, for a person who can only use his voice to operate it? Leaving all the section 508 compliance aside, is it compliant? Is it nice to look at? Does it turn dark mode on when you are in a bad lighting area? Right? All these questions come to mind when measuring this, but has any one of us actually sat down to measure these things? Efficiency. I'm sure all the techies in here would love to say, I use very little RAM and my software runs so fast, etc., etc. But really here, did you ever sit down to measure and do capacity planning and do performance testing on the time taken to do a function and the CPU, RAM, and hardware that is required to achieve, hard drive storage that is required to achieve this function? Maintainability. Can the software be analyzed? This goes back to your question, Asamer. When a system becomes legacy, how easy is it for me to analyze what it does and how it was built? Changeability. Can I change it on the fly without a lot of affecting or causing myself to do a rewrite or affecting other modules? Stability. Does it fall over all the time? Does it simply go out of service when it's hit by 500 requests? Testability. Is it testable? Can I test stuff out of this software? How are you feeling about all the metrics, guys? Does anyone actually think of these things when analyzing software that you've built? Portability. Is it adaptable to any environment? Can I run this piece of software just like I run it on Azure? Can I run it on AWS? Can I run it on premise, or can I run it in a hybrid cloud scenario? Can I run it on Linux versus Windows? Is it cross-platform? How will it run if you have a Mac client versus a Linux client? How adaptable is it? Installability. Does it take 3 engineers and 400 nuclear physicists to install the application? Or is it simply a couple of clicks here and there? Is it simple configurations? Coexistence. Can it coexist with other systems? Or you can tell me that if SAP exists in the network, and because we use the same ports that the database use, so we can't deploy this in the same place. Replaceability. Are you creating a single point of failure that cannot be replaced? Can it be replaced? This is it, guys. This is ISO 9126. ISO 9126. How many people do ISO 9126 today? Here is the bad news. No more than 5% of the software industry. And just when you thought that news was bad, I'm happy to report that ISO 9126 expired in 2011. Yes, you heard that right. You saw all these metrics that you don't do today. In 2011, it was deemed that these metrics are not good enough. They're actually not good enough. And we got hit with this beautiful document, which is ISO 010. This is the systems and software engineering quality requirement and evaluation. This is the new ISO that the big four players use to basically create some metrics around your software. Check this out. Compare this to what I just showed you. Look at how many metrics got added since 9126. So not only are we not doing 9126, but we now have at least 40 other metrics to look at, and each one of them with its own science on how to measure. And that's the only way you can get your software ISO certified. There you go. This international standard revises ISO 9126. How cool is that? So not only are we not doing the old standard, there's now a new standard that makes the old standard obsolete. All right, no more bad news for the rest of the day. Okay, standards, architecture tools, estimation, all of this stuff is cool. It's nice. It puts some structure to our pain. It puts some structure to what we need to do. But there's something else. That is the thing which makes you a real architect. Can you indeed break up a bigger problem and produce a component design that actually can be materialized into software? How do you do that? Break the problem down. This is called decomposition. And there are many ways to decomposition. This will be the last section for today. And this will tell you about the main thing that you got to think of now that you have an intro to the basics. Now you're going to think, how am I going to decompose my problem? Some of these things you've actually seen. So let's talk about them and let's see what's the best method to perform architectural decomposition. Number one, we're all got introduced to layering at one point. So we have, as usual, presentation layer, business layer, persistence layer, and database layer. Now, because we as engineers like to complicate stuff, we thought, we're going to follow what the hardware guys do. They have a host and they have an embedded hardware layers. So we're going to create more layers and we're going to follow what they do. So the result, let's do more layering. Why? Because at some point, someone must have told architects that you get paid by the layer or something. But this wasn't enough. Let's go even more. More layers. And when Sun and Microsoft got their hands on this idea and they thought, what can I do to sell more products? Let's create more layers. Do you see where the problem is? That none of these layered diagrams that you see gives you any way to decompose anything in other than one way, and it is decomposing it by technical functionality, meaning this part does UI, this part does some business logic, and this part does database, and this part does some service interfacing. So what we're going to do is we're going to create a layer per technical functionality. This does not help me create an algorithm to calculate interest in a bank, nor orchestrate the workflow of a booking in an airline system. What it does give me is it allows me to differentiate technical categorization of components in my system. So what does my layering look like? My layering looks like this. All right. So I spoke about CQRS again and again, right? So what does this mean? It means that I'm going to use layering to decomposition, except in my way. I'm going to say I've got commands that go into an application layer, and I've got a write domain which encapsulates all the business logic on my right side. Thank you, achieve data consistency in my infrastructure. Then from the write domain, I'm going to acquire things from the read domain to produce, again, projections that then I can use queries to read from. So all my layering decomposition is based on CQRS, identifying the 3 types of operations we spoke about and organizing them within 3 very distinct, what I would not call layering more than vertical or horizontal components, or whatever shape you like to call it. As an architect, I stepped away from shaping my components. This is it. I have an area which handles my writes, and I have an area which handles my reads, and I have communications between those areas to get my stuff or my operations organized and delivering functionality. All right. Now, finished with layering, now we do distribution. So what is distribution? Distribution is when you as an architect and make a decision around decomposing your software based on computational resources that you have in place. So you have 2 servers here, a rack over there, etc. So you look at your entire hardware infrastructure and you say, let me organize my software in such a way that it can be deployed on the hardware that I have or the hardware that I would like to have. Now, please note, if a system is decomposed by layering, it is not automatically decomposed by distribution. It is not meaning that every layer goes on into its own computational resource, right? That is not necessarily what we're saying with layering. With layering, we're simply saying there are different hierarchical layers that organize the technical categorization of the functionality or of my components. But when it comes to distribution, we're saying that whether layering or no layering, I've got components that are organized around how much computational resource do they need. Next, we've got exposure. How is the component exposed? Is it via an API? Is it via a service bus? Does it talk directly through some gRPC protocol to your mobile, to this, to that? How is my functionality going to be exposed? And based on that, we start creating connectors and APIs and other sorts of stuff. So even within the enterprise, we look at API consumption as consumption. This is how I'm going to use an API, and this is how I'm going to expose it. When you understand the consumption and exposure of it, then you can lay down software components in such a way that maximizes your exposure, simplifies your consumption. This is another way of decomposing your software. Next, we've got one that everyone is familiar with: functionality. Functionality is basically me saying, so I'm building a software for a retail system. Automatically, I'm going to have a marketing component, an inventory component, a sales component, and a component that handles loyalty, for example. Bang, 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 bang. And my software now looks exactly like my departments in my company. Sometimes you go even further down and you decompose the components even more with more granular functionality. And you say, for example, within the marketing department, I will have the advertisement component versus the some other component that's used by the marketing department, like a budget tracking component. All right. So another way of decomposing software is by functionality. Then we've got generality. It sounds fancy, it isn't. It's basically what most architects and developers do, is them wrapping the stuff that they can see reuse of, and they take everything that can be reused and create this fabulous library of reusable components that can be reused by any domain or any module or any other component, right? Sometimes it's not even technical. So for example, in an enterprise, you can end up with a accounting domain or an accounting requirement being a requirement of many departments. So you go and you create a reusable accounting, package, module, service, whatever you want to call it. So you decompose your big problem by seeing what out of this problem, what component can I build that can be reused by as many as possible other components. Then we come back to our friend coupling and cohesion. It says that things that work together should stay together. And things that do not need to be together should not be together, as to not create a coupling. What does this mean? Let's give a very, very solid example. Coupling is when I say that because I'm tracking a marketing budget, I'm also going to bring the accounting module into my domain. In reality, if you're tracking a budget, you can always publish events, publish commands, publish whatever you need to say that, hey, you've given me an allocation of a budget and I've used this much. If you bring the accounting domain into the marketing domain, what ends up happening is now marketing cannot change at will because it is bound to the changes. The accounting domain cannot change at will because it is bound and coupled to how marketing works, because now marketing is using the accounting algorithms to manage the budget, which is wrong. What we should have done from the start is kept accounting as an external system, a reusable domain outside my domain. But within my domain, I kept only the marketing logic, which might include the marketing budget and managing that budget without muddling the concepts of accounting as well. As for cohesion, it's the whole other way around. If because I need in the inventory department to be able to manage invoices, and I need customer ledgers, and I need stock and order invoices. But every time the inventory department wants to get that data, it has to go through a chain of responsibility of hoops and loops to get to the accounting, to get to the ordering warehouse, etc., etc. So we're saying we need a cohesive interface, and these things need to be as close as possible to each other, because guess what? Inventory cannot be tracked with stock value, etc., unless it has as a dependency an understanding for purchase orders and all the history of acquiring stock. So this is where an architect needs to identify what is loose coupling and high cohesion, and when achieving the right ratio of coupling and cohesion, it basically means that they have achieved a high ability to respond to change. Going back to our standards, you will see that there were two metrics. One is changeability and one is maturity, and both are going to go absolutely high if you achieve the right ratio of coupling and cohesion. All right. Now, volatility. The hardest and the most powerful, but it's not going to be our last. So volatility says that unlike functionality, where you're basically decomposing based on the functionality of a component, you don't do it like that. You basically decompose based on how do you anticipate the component changing. What are the potential changes in how we manage our marketing budget? What are the potential changes in how we're going to issue tickets for an airline system? How is it possible that an interest and the way we calculate interest on a loan is going to change in the future? How is the process of us consuming movies going to change from Blockbuster to Netflix? This is where functional decomposition and volatility decomposition different. In functions, you are asking what are the features and functionality. In volatility, you're asking what are the business areas and what are their ability or probability of change, and you're architecting around change, not around functionality. This a bit goes into Samer's question about the agility. Volatility architecture and decomposition is way more agile than what functional decomposition is. Why? Because change and agility are a first-class citizen in volatility-based decomposition. And it is by far the hardest and the one that requires most talent and skill and a very strong understanding of the business, not of the features. And this requires senior architects that could, in fact, again, going back to Mohammed's question, as per the different types of architecture and how can you identify areas of change. The last two. The last three. Configuration. And hang on, Omar, with all of these, why are you giving us configuration as a way of decomposition? Because guess what? Every time you have ever built a CMS, that was architecture by configuration. When configuration itself helps you shape the functionality that you're going to produce, when configuration itself drives how a certain module is going to react or be loaded or unloaded or any of that good stuff with CMSs, ERPs, etc., that is called configuration decomposition, where you decompose your software based on how certain areas require configuration and require a permutation of configurations that then drive the functionality of the system. Planning and tracking. People do not believe that. That sometimes, and I'm sure many of you have had this, where you're basically working in a company and then the architecture is kind of driven on its dependencies and everything by the project manager. So the project manager went out to the client. They gave him a project plan so that he signs a piece of paper and then he gives you the money for it. And then comes back to the project team and says, by the way, we sold the software. Please build it. It hasn't been designed yet, but here is the project plan. Now, let's turn it the other way around. How can we use this decomposition properly? It's the other way around. It's where we, as the architects, have received the requirements and we have a wish list of project management things required by the stakeholders, and based on that, we create some architectural design plans of implementation to match the project plan. And it takes a lot to basically be able to marry those two worlds together, where the stakeholders are happy, the architect gets enough time for design, and the project manager is doing that linking between them. It takes time, but it is also a very good input into the architecture process. And the last one is work assignment. Believe it or not, some people until today will say, who do we have on the team? We have Tom, and Tom is great in SQL. And we don't really have these strong backend guys, so let's put all the business logic in the database. Or we have amazing JavaScript guys, so let's put all the logic in JavaScript. Let's go with Node.js just for the fact that that's the kind of skills we have on the team. That is not scientific decomposition. Scientific decomposition is where I, as an architect, would say, I have a data expert on that team. I'm going to try to encapsulate the data work in such a way that I get the experts working on it so that my C# backend guy can continue working on the stuff he's actually good at, Java, C#, Python, and his backend, while I get my JavaScript guy ripping it on the front end, and while I look at all the people around me and see who has had experience with e-commerce before. I've got an e-commerce module here. Then you guys, please come across and do this e-commerce bit because you have a lot of experience with the patterns that I would need here for e-commerce. That is good work assignment, not deciding on a technology or on a solution based on the people you have on the team. So guys, just going back to the first slide. The $1 million question that I usually get is, so what out of all these beautiful layers, etc., more and more and more and more, like we've been through 20 slides in such a short time, which one of these? Just give me the answer. Which one of these should I use? The answer is simple. All of them. All of these feed into your architecture. They give a different angle to the solution. They give a different angle to understanding the problem. And you can use some of them to scrutinize the others. You can definitely use volatility to scrutinize functionality. You can use distribution to scrutinize your layering. You can choose your tracking and work assignment to scrutinize your planning. Exposure can be used to scrutinize configuration. Once you're an architect, these are the decomposition methods you have in your toolbox. If you have the time, and I understand you won't always have the time, but if you want that perfect diamond titanium plated model, then you need to look at your problem from multiple angles, and then you need to scrutinize your model from multiple angles. And the way to do that is to use what you see here. The idea is quite simple. The more methods you get time to apply, as the more time you get to scrutinize your model, the better your model is going to be. And with that, guys, I would like to thank you very, 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 very much. I'll take another 10 minutes of questions, and then we'll move. We'll end this here, and I'll give another, say, 5 minutes if you have any questions to post. And I'll see you on Clubhouse, hopefully in 20 minutes. And I'd like to thank you all. And if there is any questions, I'll take the questions now, and I'll stop the recording. Thank you.